Okay, we're going to pick up where we left off in the last video. Let's talk about the absolute minimum again. By the extreme value theorem. So the extreme value theorem says that if g of x is a continuous function, and remember g of x is the area function under f of x, the curve of f of x, and it is continuous. There's no place where the area doesn't exist. So g of x is a continuous function on a closed interval from -5 to 4. So there must be an absolute min. Where does it occur? It must occur at either a critical value or an endpoint. So we've already seen that the critical values are at -4, 1, and 3. And the endpoints are at -5 and +4. So I listed all of them in the table there. This is normally the way we find an absolute min or max. We find the critical values, the endpoints, and we list them. Now, I want to evaluate g of x for each of these. Now, this could take some time, and I don't necessarily have to find each one of them. For example, if at x equals 3, if I have a relative max, I don't even have to find out what that value of g of x is there, because that can't be my absolute min. And you can see that at x equals 1, I have the same thing. G of x is increasing, which means I'm adding area, all the way up to 1, and then it becomes stationary for an instant, and then I continue to add area after that. So there's no way that that can be an absolute minimum either. Now if you notice that at x equals 4, well, the area between x equals 2, from 2 to 3, and from 3 to 4 are exact opposites of each other, which means that those two areas will cancel each other out. So at the end of x equals 4, or g of 4, that has to equal g of 2. And g of 2 is not a relative maximum, but it is neither relative minimum. We definitely don't have a minimum there. I don't have to worry about calculating that value. Now at -4, let's come over to the other side. Between -3 and -4, and -4 and -5, notice that I have equal areas but opposite signs, so those two will zero out again. So I can say that g of -5, which is defined to be the integral from -3 to -5, but again I'm going from right to left in this case, is equal to the area from negative, it's equal to the negative of the integral from -5 to -3, but the integral from -5 to -3 is just 0. And so there we can see. Now it is possible that that could be the minimum value. It's not going to be, but I still write that down. Now the only other place that we need to test is at x equals -4. And in a similar way, g of -4, which is defined to be the integral from -3 to -4, is the opposite of the integral from -4 to -3, which turns out to be to have a base of 1. It's a triangle with a base of 1 and a height of 2. So it has an area of 1. And so g of -4 is going to be -1. Now we could have actually gone ahead and calculated g of 1. It's very possible to do that. It would have been 9/2 plus whatever we'd have to subtract from a square area, a quarter of a circle. We could have done that, and we could have found the area at g of 3 and also at g of 4. All of those are possible. They would have taken some time though to do that. So I'm trying to do this in as quick a way as possible. So we don't have to necessarily show every piece of work if we can demonstrate that those clearly couldn't be the absolute mins. So we don't have to worry about them. So I think we're done. In this case, the absolute min, the absolute minimum occurs at g equals -4, and its value is -1. Right? And for part D, we're going to have a point of inflection when g prime prime of x changes sign. G prime prime of x is f prime of x.